Right, so as you can see, there are 4 modules in this unit. The first module is statistics. So it equips you with basic skills in how to perform descriptive and inferential statistics, or whatever. So we'll come to that later, okay? And then module 2 focuses on how to explore the data set, how to basically wrangle it. Wrangle means how to prepare it, transform it in a way that um, that makes sense to analyze. Module 3 covers how you can make prediction, how you predict what kind of model that you can use if you want to predict certain things. Okay. And module 4, the last module, covers probability. So each module covers about 3 to 4 weeks. Okay, so as you can see, module 1 that covers week 1 to week 4. Right. Okay. So that's how the learning materials are structured. Let's look at the first one. We are now in week 1. There is an overview to the module, so it basically tells you what the module is all about. We can skip that. Okay. So let's look at the introduction. So each week has 3 sections. One is overview, where I give you some basic ideas what this topic is all about. And then the learning materials is where you find detailed explanations of the concepts. That may include formula or examples and so on. So you find that there's no slides. I don't use lecture slides for my units. Okay, so what you find is actually like an article. So I write the materials in a certain sequence that I think makes sense. So a lot of times with the lecture slides is that it cannot convey the flow of the ideas well. So I prefer to present it in a blog or article form. So that's probably how this unit is presented differently from other units. And then it will be followed by practicals. So here we'll give you a few tasks, and tasks that are typically completed through Python programming. Okay, and the practicals will also contain the solution. So with every Python programming exercises we have, you find the solutions right away, right? So in case you're stuck, you can always refer to the solutions. So that's how the learning materials are structured. So I hope not to spend more than an hour on the theory, okay, before we move on to the practical. So this is an intro to data science. So that's what this is all about. And I'm also going to cover the end goal of this unit. So I like when I learn something, at least for me personally, I like to know where I'm going to end up with. What's the ultimate goal at the end of this unit? So I'm going to show you. We're going to jump straight to that end goal, okay, without going into too much detail. So today we're living in the world of data, right? So a lot of decisions that affect our lives are made based on data. So whether you are approved for a house or mortgage or not, that could be based on your credit score, which is data, right? So whether a city goes into lockdown, that decision was made by looking at the COVID trend, for instance, right? So a lot of decisions that affect our lives are really the result of analyzing some sort of data. So data science is really about analyzing, having that ability to understand data, analyze them in the right way, right? But what separates data science from your traditional statistics, if you have taken any statistics course, is the element of programming, okay? So by its very definition, it's not possible to learn data science without acquiring some level of programming. So that's what you will learn through this unit. So if you look at this diagram, okay, so there are 3 essential skills to data science. The first skill that you need is some knowledge of statistics. Okay, so statistics could be as simple as counting the average of certain things. Okay, that's statistics. But it's not enough. You need to be able to also perform those statistical analysis through computer programming, through some sort of programming language. Now, Python is not the only programming language that data scientists have used out there. It is the most popular one, probably, but you have other programming languages such as R or Stata. I think there's a new one called Mojo. Okay, that's coming up. So those are programming languages that can be used to analyze data. Why do we need this? In the past, the need for programming skills was not really crucial because we were dealing with small data sets. Okay, so you can load those data sets on Excel, you can analyze it, that's fine. But in today's age, we're dealing with millions of data nodes and so on. So you can't load those data into your ordinary Excel, it will crash, right? So you need to find a better way to deal with those kind of data set. That does not necessarily also fit in a tabular form, column or rows. It could be video data, it could be voice data. So how do you actually deal with that, with those things? So you need programming skills to manage those data and analyze them. So that's where we have that hacking skill. Now, the third important element to data science is substantive expertise or domain knowledge. So when usually the reality is that a data science problem, it is always contextualized within a specific domain. So you might be asked to analyze healthcare data. So you need to know a little bit about the problem surrounding that healthcare data. Or you might be asked to analyze transportation data, right? So you need to know a little bit about transportation. So in the projects that will be assigned to you, it comes with a certain context. So part of that exercise or part of that assessment is your ability to also gain a little bit of knowledge in that area. Okay, so to separate the domain knowledge apart from data science is unrealistic. So okay, so you need to have some level of understanding of the problem at hand. So the intersection between these three skills makes data science. Okay, so that's what data science is all about. I've put up a video here which you can watch at your own time. This is a video by a previous HIT140 student. He came to the unit without any knowledge of programming, but he ended up being one of the top scorer in the unit. So it's just to showcase that not knowing how to program is not really an excuse. We are here to help you, right? To gain that skills. Okay. So this could be so in this case he showcased the projects that he did not within the context of this unit, but as part of another unit where he applied the knowledge he acquired in this unit in that project. Okay. All right, so that's an overview. Okay, 3 skills needed in data science. You need to know statistics or maths. You need to know some computer programming, and you need to know a little bit about the problem that you're handling. Okay, that's the domain knowledge. Okay, let's look at the learning materials. Okay, so ultimately, data science is about solving problem through data. Okay, that's what it is. There are different types of problems that can be solved. Now, usually we divide these problems into 2 broad categories. The first categories involves predicting something that we don't know, right? Based on what we already know. So let's say I have a new student. I have the data that I gathered from LearnLine in terms of the level of engagement of that student with the unit. And based on that data, I want to predict what could be the score that the unit that the student will end up at the end of the semester. So I want to predict something that I don't know, right? But how do I do that? What I can do is I collect data from all my previous students. I collect their engagement level with LearnLine, and I know their eventual score for the unit, so I can apply some sort of program data science model, okay, to learn the link between level of engagement in LearnLine and the final score and make that prediction for this new student, right? So that's basically what we mean by prediction. So one way to do that, and which we will learn in this unit, is regression. Okay, regression is where you try to predict numbers, a value that is in the form of numbers, okay, such as score for the unit, maybe the height of a person, the weight of a person, and so on. Another category of problem is more exploratory in nature. So it's about finding certain patterns in the data. So we are not really concerned about predicting something, but we are primarily interested to find out something from within the data that we don't really know previously. Okay. And then in between these two tasks, there are intermediate steps where you probably need to transform your data into a certain form, because the data that you get may not always be in a form that is easy to analyze. For example, you're asked to let's say analyze YouTube videos. So you're given the video files. So you can't actually directly analyze those video files. So those video files have to be transformed into certain ways. Okay. So images, for example, have to be transformed into pixels. So you analyze the values of the pixels and so on. Okay. So those are data preparation or data transformation. And lastly, another useful exercise within data science is to visualize your data. Okay, so a lot of times when you visualize your data, you get to see something that you didn't know previously. Okay, so this regression, exploratory data analysis, data preparation, data visualization, these are the few things that we will key things that we will cover through this unit. Okay. So I just want to highlight a couple of things here. So I mentioned before, when data science is about teaching computers how to predict certain things. Okay, so for us humans, we learn from experience, right? So in this example, if you have touched fire before, you know it's hot. So from that experience, you know next time you don't touch fire, right? Or if you've been involved in a car accident, then you know next time you need to observe the traffic rules. So likewise, in data science, primarily we are teaching a computer to learn from previous data and then make some sort of prediction from on new sets of data. Okay, so this is more relevant when it comes to the predictive task. Okay, so let me just illustrate further the difference between these two categories of problem. Okay, predicting and finding previously unknown patterns in data. Okay, I'll start with probably the exploratory ones first. Okay, now the question is, we all know the terms boyfriend and girlfriend, right? How long have we used these terms? Do you think these are new terminology or old ones? So when do you think these two terms came about? Do you want to have a guess? Was it in the 90s or 70s or 19th century? What do you think? Anyone want to have a wild guess? Let's see. Someone says 50s. Don't laugh. It's pretty close. Okay? No, it's not 90s. It's pretty close to 50s. Great job, Matthew. So I'm going to show you something, okay? So some of you might know Google Ngram. So Google Ngram basically counts in terms of frequency, but it's not really represented in frequency, in percentages, but it is based on the frequency of words appearing in books. So Google Books basically try to digitize as many books in the world as possible. So from those digitized books, then you can extract the words. Okay, the n-gram basically 1 gram means one word. Okay, 2 gram means a pair of two words, two consecutive words. So n-gram means multiple words. So basically, it looks for the frequency, or it counts the frequency of terms as index in Google Books. Okay, so the topic is, when did the term boyfriend and girlfriend came about? Or when did people start to use this term? In the 1960s. So it's pretty close to what Matthew said, pretty close to 50s. It's a relatively new term, if you want to put it that way. Okay, so before 1960s, people didn't use the term boyfriend or girlfriend. Probably uh, they call this something else, or maybe there was no concept of boyfriend and girlfriend. I don't know. Could be matchmade. Um, were matchmade by parents and so on, right? So this is an example of exploratory data analysis. We are not trying to predict something. We are just trying to find patterns. So the patterns that we want to know now, in this case, is when did certain word get introduced, okay? And there is probably a decline in the usage of these two terms lately, right? So that's indicated by this curve. Okay, so this seems to coincide with the idea of sexual revolution in 1960s, right, where people rebel against the traditional concepts of marriage or dating and so on. So we can even ask when actually the concept, the word dating is used. So, but apparently dating can be, but we don't know whether this dating actually means dating between boyfriend and girlfriend, or dating in a different sense, right? So there's some uncertainty in that sense. Okay, so this is an example of exploratory data analysis. Okay, so you can actually use this Google Ngram to, if it is relevant for any other assignments. If you can add value to what you're doing, you can actually use this. Okay, now I'm going to give you another illustrations about predictive analysis to predict some unknown or future data. Okay, you see that there's an apple here, and there's obviously an orange. Okay, that's not my snacks, but they are here for a purpose. Okay. So there's something called Teachable Machine by Google that is fun to play with. So, and I find it quite useful to illustrate the concept of predictive uh, analysis. So you can basically train a computer to recognize your own image, to recognize or to predict certain image. Okay. In other words, if I show this image to the computer, it can say, "Oh, this is an apple." Okay. It tries to predict this is an apple. Okay. So I'm just going to show you how this works. So I'm just going to choose the image project because that's the one that I've used before. Okay. Standard image model. Okay. I mentioned before that we need to show previous data to the computer to learn from, right? Only then it can predict the new set of data, right? So the first step in data science is to have a data set to work with, or to train the computer with, okay? So let's assume in this case, I want the computer to predict whether an image is an apple or an orange. So I need to supply the computer with images of apples and oranges. Okay, so I'm gonna do that. because there are just two categories to predict. I will, they're just, so we call it class. So the first one would be orange. Second one, I'll call it apple. Okay. And I'm just gonna upload a few images of orange. Okay, so here are images of orange. Please learn from it. Okay, that's what we are basically telling the computer to do. Apple, likewise, I will provide it with few images of apple. Okay, just to be fair, we give 3 to each. Okay, and then train the model. So something happens in the cloud. Okay, and they think that I'm an apple in this case. Right. Right. So what you can see here, I'll just. So I'm closer to apple than to orange, which is strange. When I tried before the class, I was an orange. So I'm not sure. It could be the lighting, could be, I don't know, right? So, but because my face is the same. Okay, so as you can see, it goes by probability. So it doesn't. It's oftentimes it is not a deterministic system, meaning to say it doesn't say 100% apple or 100% orange. So it calculates some sort of probability and pick the higher probability and use it as the best prediction. So it tried to predict this is an image of apple, which is obviously wrong. Okay, so let's try with the real apple in this case. Okay, I'll just oops. Okay, right, apple, right, pretty good. Okay, here's an orange. Oops. Yep. Okay, so if we put both, let's stack them up. Uh, sometimes apple, but when I tried just now, it's sort of 50-50 kind of thing. Okay, so this is an illustration of predictive tasks. What are we predicting here? We try to predict what image this is, right, or what object this is. So the principle is always the same, whereby we supply the algorithm with a data set, and then we test it on a new set of data, right? So there are many algorithms. So in this unit, the algorithm is regression. So we are limited. So in this case, we are labeling objects, right? But with regression, we are just predicting some sort of numbers. So let's say I want to predict what's the GPA of a student, okay, at the end of the study. So that's the kind of prediction task that we can do with regression. Okay, so I hope that sort of pique your interest. Okay, so you can play with it if you want to. Okay, at the end of this class. So I'm just gonna give you probably. Okay, there are two tasks when it comes to prediction. So here, when you have a data set that when we train computer to learn from data set, it is important that we tell the computers the correct answers. So similar to what I did just now in that demonstration, I had to supply the computers with the correct images of oranges and the correct images of apple, right? So that then computer can learn what are the important characteristics that belong to oranges, probably color, shape, right? And what are the important characteristics of apple? And what are the key characteristics that separate these two fruits? And very obviously, it will be the color, right? So in our data set that we use to train computer, we need to have some label, okay? So for example, if you want to predict whether, so here you have patient information in your data set, and you have the age, gender, male, female, smoking, whether smoking or not, vaccination, and you want to predict based on this data set, based on gender, age, smoking, vaccination, whether the patient is sick or not. So we need to first have a data set that contains the correct answers. So the correct answers here will be for the first patient, 0 means not sick. Second patient is not sick. Okay, third patient is sick. So then the computer will try to learn how to link these different variables to the final outcome. Okay. Then, but there are cases where we don't have those labels. Okay. For example, we have data from supermarket about the customer. So we have customer age, the gender. Sorry, this is kind of swap. So gender should be here. Okay, marital status, single or married, occupation, student, and the product that they purchase. So we want to know which type of um, customers that usually buy certain types of products. Okay, right. So for example, an overused example would be from market basket analysis, whereby we try to find which product is often bought together with which product. So the common cited example is beer is oftenly common bought together with nappy. So it's probably, well, could make sense when you have baby feel stressed up. You just want to have a beer at the end of the day, right? So these two things are often brought together. So we are not trying to predict something, but we are trying to find things that come together, right? So this is another example of exploratory data analysis, where you need to predict something. That's predictive analysis. In predictive analysis, you need to supply the computer with data that is already labeled. Okay, so those are the key difference. So in terms of predictive analysis, we will only focus on regression in this unit. Okay, regression is to predict numbers. For example, we want to predict the results, a student score for this unit based on, let's say, the number of hours of study and number of hours of sleep that the student has. So based on these two values, can we predict their score? Okay. So again, to do this, you need to have a data set that have hours of study, hours of sleep, and the actual score. Okay. To make things slightly more practical, let's consider this example. So we will revisit this example next week through the practical, but I'm just going to introduce this case study. Right, the road trip. So you and a group of friends are planning for a one-way drive down from Darwin to Alice Springs. Okay. As this is the first of such a road trip, you've never driven down to Alice Springs before, you wonder how much should be budgeted for the 1,500 kilometer drive. Okay. Luckily, you have some data, some previous data. Okay. So you have been laboriously tracking your car's efficiency for the last year. So somewhere on your computer, there's this spreadsheet. So previously you have traveled 390 kilometers, and then you paid $36.66. In another trip, previously you traveled 403 kilometers and you paid this much, and so on. So here is the solution. So you can actually use regression to learn from this existing data set so that then you can make the best prediction for 1,500 kilometers, how much dollars you need to spend. Okay. Now, common sense, how would you actually approach this problem? Let's not talk about regression. How would you approach this problem if you have this information? Yep. Yes, find the average. I think that's probably the best way to start with, right? You can total up. You can find the average maybe by trip, or you can total up the total kilometers, total up the dollars, and then divide find how much dollar per kilometer. So you can then multiply that by 1,500. You can do that. Okay, so that's the baseline. So that might work, that might not, right? So the purpose of regression is regression by right should give you a much better prediction than just taking the average. Okay, but that's really a good one, taking the average. But sometimes the average method forgets that there are variations to each trip. So how much you spend could depend on maybe the road condition, right, or the weather, or could be the petrol price at that time. So all these are additional factors that could complicate the prediction. Okay, so that might put some limitation on your average approach, but that's really a good start. Okay, so we will use linear regression for that in this unit, and we'll see how we can do that later. Okay. So I'm coming to the end of the theory session. Just a couple of things to show here. So let's take a look at what linear regression is. So I'm going to test you in the coming quiz on some basic understanding of regression. Okay. So let's watch this video. It's just 5 minutes. Yeah, some people say average, mean. Yeah, mean, average, the same. Okay, good try. Thanks for that.
This tutorial is an introduction to regression. There's an X variable.
Sorry, let me just adjust the volume. Okay, just 5 minutes.
This tutorial is an introduction to regression. There's an X variable and a Y variable in this case. The independent variable is on the X-axis and the dependent variable is on the Y-axis. And we try to form a relationship between these two variables and draw a line, in this case a straight line. And over the next series of videos, I'll explain what all this means. What we try to understand is as the independent variable is moving or changing, what happens to the dependent variable? Does it go up or does it go down? How does it change? If they move in the same direction, if the independent variable increases and the dependent variable increases as well, like this, we say there's a positive relationship. If, on the other hand, as the independent variable increases and the dependent variable decreases, like this, we say there's a negative relationship. The line would look like this, go downward. In linear regression, we try to make a line. To make a linear regression, the key is on line right there, a straight line. You can also do curved lines, but for this topic, it's all straight lines. To actually conduct regression, I take observations, and I'll just plot some more observations in here randomly. I'll stick them in here like that. And I try to find a line that will fit, a straight line that fits to all these different points. And this is called my regression line. And it's based upon the least squares method. And in the end, I want to minimize the difference between the estimated value and the actual value. I want to minimize my errors. This line will have a lot of errors if I compare the actual to the estimated value. And again, the point is to minimize these errors or make them as small as possible. Now let's imagine I put study time on the x-axis, or make that my independent variable, and the dependent variable becomes grades or GPA. As study time increases, grades should go up. There is a positive relationship. In regression, we develop these equations like this. In this case, y hat is estimated grades, and it's based upon, or it's equal to, b naught plus b1 times x, where x is study time. B naught we derive mathematically, and it is the y-intercept. B1 we also derive mathematically, and I'll do it in a later video, and it's the slope of the line. In this case, the slope is positive. In the next video, I'll discuss how you develop these equations. Now, if I change the x-axis to time on Facebook, we see a negative relationship. More time on Facebook, grades will suffer and go down. A negative relationship. What we're estimating is still grades. Estimated grades is equal to b naught minus b1 times x, where x is time on Facebook. B naught is still the y-intercept. The y-intercept. And it is a calculated value. The slope of the line is negative b1 because it's downward sloping, negative relationship. And as I said before, I'll show you how to calculate this equation in the next video. The x is the independent variable. The y is the dependent variable. The x is what we control, what we manipulate, what we change. And the dependent variable is the outcome. So study time is the independent variable. It's what we control and manipulate. And your grades are dependent upon how much you study. Now this looks really ugly, and it's what I'll talk about in the next.
Right. So there are a few things here that I need to unpack, okay? Based on what we have watched in the video, let's bring it back to the previous example of road trip. Okay. So we have this data set, and each of this row is an observation. In other words, we observe that when we travel for 390 kilometers, we paid this much. When we traveled 403 kilometers, we paid this much. Okay, so each of these is an observation or data point, we call it. Now, in this case, how many observations have we got? 19, yeah? Because the first row is for the header, right? 19. Okay. So if we plot that on the regression chart or on the scatter plot, we call it, similar to the chart that you saw on the video. Okay. So we may get something like this. Right? So the horizontal line, we call it the x-axis. We usually represent the x-axis use x-axis to represent the independent variable. Independent variable, there are two concepts here, independent versus dependent. Dependent is what we want to predict. Okay, so in this case, we want to predict the amount of dollars spent, the budget, right? So that is the dependent variable. Okay, we call it also response variable, and we represent it along the vertical line, the y-axis. And then the value that we base the prediction on is usually lying on the x-axis. So in this case, the number of kilometers. So you mentioned that there are 19 observations. So then we have 19 dots here. 1, 2, 3, 4, 5. If you count it, there are 19 dots. So each of these dots represents the row that we have here. Okay. So for example, the first one, let's say $36 correspond to 390 kilometers. So that is probably So 390 kilometers, that's somewhere here, $36. So that's probably this one. So the first row is represented by this dot. Okay, so you have 19 rows. So the dot is really the intersection between the two values, the kilometer and the dollars. Okay, so when we do the prediction with regression, what we want to do is to draw a straight line through these dots. So you saw the same thing happening in the video. So what we want to know is, can we draw a straight line through these dots? So this straight line, what gives the regression the name linear regression? So it's always straight line. Okay, now obviously there are things that can be modeled not through straight line, but that's not really our concern here. So linear regression will always try to find the straight line that goes through these dots. Okay, so this straight line can be mathematically represented by the regression equation, such as this. Okay, so the straight line basically is form the basis of our prediction. So we can then ask, if we travel for 400 kilometers, how much dollar should we spend or will we spend? So you start from 400 kilometers right here, go straight up until the point where you meet the straight line, and draw a straight line to the left, and that's how you get the corresponding dollars. Okay, so it may not be the best or the most accurate prediction, but this straight line will probably give you the most reasonable estimation. Okay, so it is very accurate, let's say, for this particular data point, right? So when a straight line goes through this observation, it means that the prediction is pretty accurate. But there are some other prediction that is not quite accurate. So for example, for this, we travel this far. By right, according to this straight line, we should only pay this much, right? But the data shows that we actually pay this much, right? So there's some amount of errors that exist in this regression. So the question really is, find the best straight line that will minimize the total errors between the line and each of the points. Any distance between this line and the data points represents some sort of errors, right? So you want to find a straight line that try to minimize that errors, because in theory you can actually draw many straight lines through the data points, right? You can draw it this way as represented by the green line, or this way by the red line, or many other ways. The question is, which one is the best line? The best line is the one that has minimum errors. Minimum errors means you take the difference. Let's start with the green one. If you follow the green one, any difference between the green line and the actual observation is an error. So this is an error. Here is another error. So you total up the errors. Here is another error. All this distance is an error. So you total up. So find the straight line that has minimum total errors. So that's your best line. Okay, so that's the logic behind linear regression. Okay, so I'm jumping very far ahead here because this is the subject of week 8 and 9. Okay, but I just want to show you the basic intuition behind linear regression, right? But then we will learn how we actually do this mathematically speaking. Okay. So just another example before we close this part of the workshop. Here is another example of a linear regression line. Okay, quick question. Which one is the dependent variable? Accumulated savings, correct? Because that's represented along the y-axis. Time and weeks is the independent variable. Okay. Which one is the response variable? response variable is the same as dependent. So in this case, accumulated savings, basically the variable that we want to predict. So here we probably want to know, as we save for how many weeks, then what is our total accumulated savings? Okay, that's captured by this straight line. What are these vertical line between the regression line and the observation? Errors, right? So how do we get the total errors of this regression line? You total up the amount of, you total up each amount of errors that we have here. Okay. Um, so this errors is basically the difference between the predicted value and the actual value. So if the actual value is 20 and you predict it to be 18, so your error is 2, right? Because 20 minus 18, 2. Okay, so that's the difference between actual value and the predicted value. That's the errors. How about the 400 here? So here is, you've seen this equation earlier in the video as well, the B naught or B0. That's called intercept. Intercept basically is the point along the vertical axis, the y-axis, where the regression intersect. So 400 is basically refers to this point, 400. Okay, so that's the value of savings when the weeks is 0. Okay, so that could be the amount of savings that you start with before you start counting. Okay, so intercept is the value of on on the y-axis, the vertical axis, when the value on the x-axis is 0. That's the meaning of intercept. Okay. How about this? Okay, another question. Sometimes this can be a plus sign. Sometimes it can be a negative sign. Plus sign means it is a positive relationship. There's a positive relationship between these two variables, meaning as the time increases, then the accumulated savings will also increase. Or the time decreases, then accumulated savings will also decrease. So they move along the same direction. If it is negative, that indicates negative relationship. Negative relationship means these two variables move in the opposite direction. If time increases, then savings. So if time increases, savings decrease. Okay, but obviously in this case, the reality is that this is gonna be a positive relationship. Okay, most of the time. How about the 307.50? That's the coefficient. What does it mean? This is the amount of change in the savings if you increase the weeks by 1 unit. If you increase the time by 1 week, then the savings will increase by this much. Okay, and this happens to determine the slope. Okay, the larger this value, then the slope will be steeper, because a slight change in the time, it means a large increase in the accumulated savings. Okay, so that's those are some of the key component in regression. All right, so as I mentioned, this is really the end goal, one of the end goals of the unit, because if you jump straight to module 3 in week 8 and 9, that's where we really talk about how we get to linear regression, how it comes about. But I have told you the basic intuition, the basic concepts of linear regression, and I'm gonna test it in the online quiz. Okay, so what we covered today, okay, this simple basic concepts. Yeah, questions from the auditorium? So I hope you, am I going too fast or is it clear enough? Yeah, can you understand? Okay. Yeah, let me know if there's any question later. Yeah, why is the line not starting from 0? Yeah, that's a very good question, I would say, because sometimes it doesn't quite make sense to um, to have the intercept to be 0. Okay. Right. Going back to the previous illustration of road trip, right? There are two regression lines here. What's the difference between, okay, let's look at the equation here. The green ones, here is the equation. The intercept is $8. So remember, intercept means the value along the y-axis, in this case, the Australian dollars. So $8. So you basically paid $8 when the kilometer is zero. Even if you don't travel, you actually paid $8. So it doesn't quite make sense, reality speaking, right? Okay. So we can actually force regression to set the intercept to zero, because that sort of capture our basic intuition about, driving, isn't it? You don't drive, you don't use the petrol, right? So this means you don't pay any dollars for 0 kilometers. So that's to answer that question, yes, we can set the intercept to zero. Okay. But a lot of times, if we are more concerned about getting the prediction right, sometimes we have to sacrifice that sense of reality for a better regression line. If we find that the green line produce a much better, a more accurate prediction than the red ones, probably we just want to go with the green one, even though the intercept doesn't kind of make sense. Okay. But under certain circumstances where you're really particular about, okay, intercept must be zero, there is a way to force it to be zero, but it may not necessarily give you the most accurate prediction. Okay. Okay. If there's no question, we're gonna take a 20-minute break. Now, what you can do during the break is, if you want to participate in today's practical, so we will basically teach you how to set up Conda environment, how to do simple Python programming, how to use variable, how to print out variable values, and so on. If this is something that if this is something that if you have actually learned this in other units, you might find it very basic, so you may skip this practical. That's fine. Okay. So so if you want to participate in the practical session later, I need you to do the following. So during the break, where you have 20 minutes, please download and install Anaconda. Anaconda is a software that allows you to easily manage Python packages. Okay, so you don't have to worry what Python packages actually mean. If you're not familiar yet, we'll talk about it. For Windows user, you can find the installation steps here. If you're a Mac user, I have provided you with a link to how to install on Mac. On Mac, once you have installed Anaconda, please also download and install Microsoft Visual Studio Code. Okay, VS Code stands for Microsoft Visual Studio Code. That's the software that allows you to write your code. Okay. So installation steps are available right there, depending on whether you are working on Windows. I'm not a Mac user. My level of support for Mac is kind of limited. Therefore, I have given you some of these installation steps, as well as some additional instructions how to install Anaconda on Mac, as well as a YouTube that showcase how to also install on Mac. So these are the instructions that are available for Mac users. Okay. Okay. So if you look at the exercise, is pretty simple. I'll go through with you how to set up Conda environment, how to install Python packages, and so on, and then how to write a simple Python program, how to print output, how to use variables, how to write a function, and so on. Okay. So some of these could have been covered if you are taking software now, HIT137. So that might be covered already. So if you don't find this exercise to be necessary, by all means, you can skip the practical for today. But if you're new to Python, no idea what to do, then I highly recommend that you stay on. Okay. So there's flexibility here. You can participate. Hi guys, to my right. Let me finish. Okay. There's flexibility in this in how you want to participate in the final section for this workshop. You can either participate. You can, if you want to do it at home, you can do that, or you want to do it from anywhere from campus where you have easy access to power outlet, you can do that as well. Okay, or if you want to do it here with me, you're welcome to do so. Okay, it will still be recorded. You can always watch it again later. All right, so we'll be back at 4:10. Okay, 4:10 p.m. So we have 20 minutes for the break, as well as to download and install the software. You can use, yes, you can use.